though. No class on Monday. I've actually canceled the Zoom meeting. I was explaining to Adam, I have a dentist appointment, both myself and my son. And if I try to reschedule it, it's like 4 months out. So I'm just going to go ahead and keep it. I was looking at the schedule anyway, and because we have a review to date next week, it works out really nice anyway. I really would have only had 3 lectures. So no class on Monday, just take the day off. Don't worry about it. We'll start section 3.5 on Tuesday and Wednesday, and it's due on Wednesday night, so it works out well. Don't forget that this Saturday you have section 3.3 and 3.4 due, and then we have quiz 3 that's on Sunday in MyLab Math. So today we're going to do section 3.4. There's a lot of stuff in this section. It's not necessarily a difficult section, but again, it's crammed full of information. So we're going to talk first about the library of functions, and then we'll go graph piecewise functions. So I did send out a handout that has the library of functions. I tend to refer to that library as our toolbox functions. So these are the ones that you should know, and you need to know them immediately. So they're the ones that are going into your toolbox that we will use a lot moving forward, and not just my class, but every class after this one, you're expected to know these functions. So they're going into your toolbox. They're not necessarily in any order. The first one we're going to call is the identity function. And we have already talked about this in a roundabout method. But what it is basically f of x is equal to x. And again, don't forget that f of x is the same thing as y. So you can think of this as y equal x. Its graph cuts through the origin at a 45-degree angle. So basically 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, and so forth. The reason it's called the identity function is, believe it or not, if you can fold something across this, it has symmetry to the origin. Now, we've been talking about symmetry to the origin of being a double fold. So double fold means that you fold this piece down and this piece over on top of itself. So we've been using this identity function as a symmetry to the origin or an odd function. We just haven't done it that way. The other reason it's called the identity function is whatever you get for x, you also get for y. In terms of things that we've already talked about, its domain and range would be all real numbers because it goes off in infinity in both directions. It's got a slope of +1. In terms of intercepts, both the intercepts are at the origin. It's always increasing. We already told us that it was an odd function. So that's the identity function. We'll use it more in chapter 6, so we do need it. The next one, number 2, is just a constant function. Not very exciting, so constant function. So this would be f of x equal to some number. I'm going to use a b to represent the number. And this is coming from basically y equal mx plus b. We're saying that m is 0. So it's just a horizontal line at wherever you say b is. So if this is my x and this is my y, up here at some value b, I would have a horizontal. That's a constant function. You'll notice they're both functions because they both pass the vertical line test. In terms of its domain, it's all real numbers. Its range is just that single value at b. So if you were to write the range for this function, you literally would use just set notation with whatever the number is in braces because it's a single value. It's a constant function. It is even because it folds across the y-axis, so it has symmetry to the y-axis. So those are the first 2. You've seen those in the past. We haven't really talked about them much, but you've definitely seen them in the past. Then we'll move on to some newer ones. And again, the handout has all of these and all of the information on these. So it's actually one that if you can print out is pretty handy to have. So the third one we're going to call as the square function. So we're talking about f of x equals x squared. So its graph, we've talked about this before, is a parabola. So again, this is called parabola. Looks like parabola. We'll spend a whole day in the future at the beginning of chapter 4 talking about this, but it's a parabola. We've graphed a couple of them by plotting various points and so forth, but from here on out, you now know, we've established that if you have an x squared, it graphs as this U shape. So in terms of information, the domain would be all real numbers. The range would start at 0 and go up to infinity. The intercepts are at the origin. It's decreasing on the left side. So if we had to write the decreasing in, so DEC for decreasing, it would be decreasing from negative infinity to 0. And then it's increasing from 0 to infinity. It's an even function because it folds across the y-axis, so it has symmetry to the y-axis. And that's our square function. So from here on out, when I say x squared, you automatically think a u shape. Number 4 would be the cube function. So that would be f of x equals x to the third. You could actually plot any of these by hand by just plugging in values for x and y. -2, -1, 0, 1. Just plug in values. This one ends up looking like this. Goes through the origin. You've got a point at 1, 1. You've got a point at -1, -1. It's a nice, smooth, continuous curve. It's also a polynomial. Both of these are polynomials because they're continuous and smooth. When you talk about this one, its domain and range are all real numbers because the arrows on both ends are going off in both directions, left to right, up and down. So intercepts are at the origin still. But this one's always increasing. So if we wanted to talk about increasing on this guy, we would say from negative infinity to infinity. It never goes downhill. It only goes uphill. In terms of symmetry, it would fold across the origin. If you double fold it, it will fold onto itself, which means it's an odd function. And that makes sense from those exponents. The other thing to talk about in terms of this is the fact that, and I just lost that train of thought, isn't that terrible? Oh, we call this an S shape. So in the future, when we talk about a cube, we'll say it's an S shape, even though it doesn't look like an S. We need something to call it. So we're just going to call it an S shape. That's the next two. And again, they're not in any order. They're just ones we need. So they are all in the textbook and on the handout. The next one, I still think you've dealt with before, is the square root function. The square root function. So f of x is equal to the square root of x. And again, to get this, I would come in and plot some points. So if I plot 0, the square root of 0 is 0. If I plot 1, the square root of 1 is 1. And then I'm going to skip up to 4 because the square root of 4 is 2. And we're going to end up with something that looks like that. So it looks like a half a parabola, but only the path that occurs in quadrant 1. Now, its domain and range are a little bit pickier. Its domain is going to start at 0 and go off towards infinity. Because the origin is an actual point, it's going to be a closed bracket. The range would be the same. So in terms of the bottom of the graph is at 0, the top of the graph is at there at infinity. It's always increasing. The intercepts are at the origin. In terms of symmetry, it has no symmetry, so it's neither even or odd. It's one of the few that we talk about that's not even or odd. And that's because it has no symmetry. And I have no name for that. We just call it a half a parabola. It's the square root function. And if we can do a square root, we should also do the cube root. So number 6 is the cube root function. Cube root function. So f of x is equal to the cube root of x. And again, the same thing would be going on. You can plot points. Please recognize that this time you can also plug in some negative numbers. So the cube root of 0 is 0. The cube root of 1 is 1. But the cube root of a -1 is -1. And then I would actually skip all the way out to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Because the cube root of 8 is 2. The cube root of a -8 is a -2. So it looks like that S we saw just a few minutes ago, but turned sideways, and that's the cube root function. Now, I know in our 101 class that we talk about the square root, the cube, and the cube root. So for some of you, they're not new. In terms of information, its domain and range are going to be all real numbers. The intercepts are again at the origin. This one is increasing all along its length. In other words, if I walk, I'm always going to be walking uphill. So it's increasing from negative infinity to infinity. Symmetry would be over the origin, so you can double fold this and fold onto itself, which tells us it's an odd function. So, okay, you've seen all of those before. There's no exciting anything in any of that. So let's talk about a couple that you may not have seen before. And that would be the absolute value function. So this is number 7. Absolute value function. And we did talk about absolute values clear back in chapter 1. So f of x is equal to the absolute value of x. Again, you can plot points with this. You plug in 0, the absolute value of 0 is 0. You plug in a 1, its absolute value is 1. If you plug in a negative 1, its absolute value is 1. Look at this beautiful V shape. So we know that absolute values graph is a V. So yeah, it's one of the few that we graph in our class that is not smooth and continuous because it's got a sharp point. It's not considered to be smooth. So which really doesn't impact us, just as a comment. The domain and range, the domain is going to be all real numbers, but the range, notice, is going to start at 0 and go off towards infinity. The intercepts are at the origin. In terms of increasing and decreasing, it's split, right? So it's decreasing on the left side, so negative infinity to 0, you'd be walking downhill. It's increasing on the right side from 0 to infinity. And symmetry would be across the y-axis, which makes it an even function. And there's our absolute value. So it's kind of handy. We won't do a lot with it other than today and then next week. We won't see much with it. Number 8 is the reciprocal function. Reciprocal function. So that would be f of x is equal to 1 over x. So it's called the reciprocal because you put x into the denominator. So we know that that's an inverse variation relationship. Okay, this one, a lot harder to plot points because you have to be pretty specific about what you pick. I cannot plug in 0 because I can't put 0 into the denominator of that fraction. So I can't use 0 at all. I can plug in a 1. 1 over 1 is 1. Not very exciting. I can plug in a negative 1. I'd get a negative 1. Now, if I plug in a 2, I'm going to get a half. So that'd be 1 over 2, which is a half. If I plug in 3, I'm going to get a third. So we can see that it's going to get closer and closer to this axis. Well, if you plug in a fraction, then you'd have 1 over a fraction, which is 1 divided by a fraction, which is 1 times the reciprocal. So when you plug in a 1/2, you're going to get a 2. So it actually ends up looking like this. So it looks something like that. And I asked a class a while ago what they would like to call that, just so we would have something to call it. And somebody said, oh, it looks like a bow tie. So ever since then, I call this the bow tie function because it kind of looks like a bow tie if you turn your head sideways. So it's very restrictive in terms of information. Both the domain and range are going to go from negative infinity to 0 with a parenthesis, and then 0 to infinity. Because again, you can't plug 0 into the denominator, and there's no way to have it ever equal to 0. There are no intercepts because it doesn't cross either axis, so no intercepts. It's always decreasing. So it's decreasing from negative infinity to 0, and then again from 0 to infinity, it's decreasing. So you're always walking downhill no matter where you're at. It is folding across the origin, so it's an odd function. It's different. We will do a lot more with rational functions in a later chapter, but it's different for us. It's pretty new for all of us. Now, your book doesn't discuss it, but I think it's worth bringing into play here. A kind of ninth function that we're not even going to really title, but if I ask you to graph f of x is equal to 1 over x squared, it's going to take this piece that's down here and bring it up. So if you're doing a reciprocal function where the denominator is squared, you'll end up with the two pieces on the same half, the top half. Can't be on the right or left because it wouldn't be a function, so but on the top half. So if I had 1 over x cubed, it would come back and look like this. 1 over x to the 4th would look like this. So just as a comment, because we will kind of need that thought in the future. So, okay, and those are the library functions. You basically need to know those 8, and you need to know them as soon as possible because we're going to use them for the rest of the lecture. Okay, and just to make sure everybody is catching it, Monday is no class. We'll have no class on Monday. I've canceled that Zoom meeting. I have an appointment that I can't really reschedule, so that was set a long time ago. So we'll just resume our class on Tuesday, and we're fine in terms of the homework and everything. We only have 3 sections next week anyway, so we'll just start section 3.5 on Tuesday. So have a nice weekend. Enjoy it. Don't forget the stuff that's due on Saturday and Sunday, though. And now we're going to go graph piecewise functions or talk about piecewise functions. So now that we have this toolbox of functions, we need to use the toolbox to graph piecewise functions. So basically, piecewise functions. So this is a function that is made from pieces of other functions. So it's basically made up of all kinds of different pieces. And in the real world, piecewise functions actually govern a lot of what we do. So if you pay any kind of utility bill, you're paying in a piecewise function. So in other words, you're charged a certain rate when you use so much, let's use electricity, kilowatt hours. And then if you go over that, they charge you a different rate because you're a high usage customer. So same thing with your water bill, same thing with your gas bill. Then you've got all those taxes and fees that are added on that add to the complication. So it's made up of different pieces. Let's see, other piecewise functions would be mailing things. So when you go to the post office and you mail something, depending on the weight, you're in one category for the weight, they charge you this. If you're up in the next category for the weight, they charge you this. So those are all piecewise functions. So we're going to start off kind of gentle. So we want to evaluate the following function. So we're going to do P of X is equal to, and I'm going to use 3 lines on this piecewise function. It's going to be equal to 5, and that's if X is less than or negative 3. It's going to be equal to X squared minus 4 if negative 3 is less than or equal to X is less than a positive 3. And then it's going to be equal to 2X plus 1 if X is greater than 3. Okay, so that's our piecewise function. So we can see that it's made up of 3 different pieces. You'll notice that these are in our toolbox of functions. So this 5 would be a constant function. Here's our parabola sitting here as a quadratic. And here's a line or a linear function. It's not the identity function, but it is still a line. So it's made up of different pieces. Now what they're asking us to do is to evaluate it. So for part A, let's go find P of negative 5. So P of negative 5. So don't forget that one input gives one output. So no matter what you do, you're only going to plug this negative 5 into one of these because you can only get one answer back out of it. So because negative 5 is less than negative 3, I'm going to plug it into the first piece. So when I plug in the negative 5 as my input, there's no X here. It just means that no matter what you put in, you're going to get a 5 out of it. So the answer is 5, and that's from piece 1. So let's come in and label our pieces so that the conversation makes a little bit more sense. So we're going to call this first piece, piece 1. We'll call this piece 2. And we'll call this piece 3 so we can communicate, basically. Okay, part B wants us to find P of negative 3. So I come back to the boundaries on these pieces. That's the inequalities over here telling me what's going on. We're doing an X value of negative 3. Well, this is only good if X is less than a negative 3, not when it's equal to negative 3, so that's not good. But over here in that middle piece, we know that X is greater than or equal to negative 3. So this is where the equal to negative 3 is occurring. So that means I'm going to take and plug negative 3 in for the middle piece for the X. So that would be a negative 3 squared minus 4. Again, The only information that we really need is which one we're plugging it into. So -3 squared is 9. 9 minus 4 is 5. And again, I used piece 2. And it's a fluke that these both came out to be 5. Just happens. Okay, what if I asked you to find p of -2? So p of -2. Well, I have to think about where -2 is. -2 falls between -3 and +3. So I'm going to plug -2 into that second piece again to get my answer. So -2 squared is 4. 4 minus 4 is 0. And again, I used piece 2. Okay, part D, let's do p of 0. So I have to figure out which piece to plug it into. So I know that 0, again, falls between -3 and +3. So we're going to plug a 0 into that same piece that we've been using for a couple of times now. So that'd be 0 squared minus 4, which is a -4. And that's because we used piece 2. Part E, let's go do p of 3. Oops. P of 3. Oops, I did copy it wrong. There's an equal to on that one, sorry. So p of 3, and that's why it didn't occur until we got to this point. So I had to know which of these two pieces the 3 occurred in. And it occurs in piece 2 again because of where they equal to. So we'll get a 3 squared minus 4. That's 9 minus 4, which comes out to be 5 again. And I'm seeing some repeated values on that piece too, because we know it's a parabola. It's that U shape. So we're kind of expecting at some point it repeats itself. And then finally, the last one's asking us to find p of 5. So finally, because 5 is bigger than 3, we're going to skip up to the last piece and plug it into here. So we'll have 2 times 5 plus 1. That's going to give me 11. And finally, we use piece 3 on that guy. So this is exactly what would be used for your utility bill. So the input would be how many kilowatt hours you're using of electricity. And depending on if you use less than a certain amount, they charge you a flat rate. If you're using between amount, plug it into a function. If you're using more than that, you use another function. Tax codes are written the same way based on your income. So piecewise functions are used a lot. They're just usually hidden in the background. Comments or questions about evaluating one? You have one to do. And now we're going to spend the rest of the time graphing piecewise functions. So I'll admit this is one of the lectures that I think is always a little sneaky, a little tricky. So what we want to do, this is example 2, is we're going to come in and graph this piecewise function, then we're going to find information from it. So f of x is equal to x minus 1 if x is less than or equal to 0. And it's going to be equal to the square root of x if x is greater than 0. So we have 2 pieces. I'm going to label them again just so we can talk about them. So here's piece 1, here's piece 2. You can have as many pieces as they decide to put into it, but mostly it's usually 2 or 3. So I've got a piece 1 and a piece 2. Before I start to graph them, I'm going to come in and talk about them so that I've got a handle on in my mind about what's going on. So piece 1 is going to be our left half because the inequality is pointing to the left. So this is the left side of our picture. Piece 2 is going to be our right side. And that's because we're pointing to the right or greater than 0. Okay, what kind of pictures are they going to look like? Well, piece 1 is just an x minus 1. So because there's no exponents, x not in the denominator, there's no radicals or anything like that, I know that that's a line. So the left side is going to represent a line. Now the right side we just established in our toolbox functions, that's the square root function. So I know this is going to be that half a parabola kind of thing. So I'm actually going to draw myself a really quick kind of note on what it's going to look like. Okay, so now that we've talked about it and analyzed it, we're going to come in and I'm going to go ahead and plot some points just to help us get a good picture out of these. So we're going to go to piece 1. That's the left side. And what we're doing is y equals x minus 1. So notice that as I'm doing this, I took out the function notation and just going to write it like a line. So y equals x minus 1. I want to make a really quick little XY table to help me get this thing graphed. The very first number that I will always use on my little tables is what we call the boundary number. So for the left side, the boundary number is 0, and that's coming from the inequality. So this boundary number is where the two pieces are being established from. So our boundary number is 0. The very first thing I'm going to do is plug in a 0. Well, 0 minus 1 is a -1. But now I have to plug in other numbers to get a shape out of this thing. So because we're doing the left side, we're going to go left of the boundary number. So I need something that's to the left of the boundary number. I'm going to go out there and use -2. So it'd be -2 minus 1, which gives me a -3. And because it's a line, that's all we need. We only need 2 points. So I'm going to come over here, and I usually find information and then go plot the information. So I have 0, -1, and then we're going to have -2, -3. And there's the next one. So I've got those 2 points in. I'm constantly reminding myself that this is the left side. So I'm going to start my picture at the boundary number and then go to the left. And that's it. That's all I've got on that side. Any comments or questions? I'm going to go back through that kind of quickly just to make sure. So again, I recognize I'm dealing with the left side, and then the left side is going to start at 0 and go to the left. It's y equal to x minus 1. We plugged in 2 different values that were 0 and to the left of it, and that gives our y values to be able to plot. I'm going to come back and just comment, because we need this in just a second, that this 0 is a closed circle, and it's closed because of the equal to back up on the inequality statement. Okay, that's my left side. Let's go do the right side. So piece 2, which is the right side. And it really does help if you think about this as left and right, because that way you don't draw things in the wrong spot. Its boundary number is still at 0. So the boundary number is still 0. But this time, when I go to graph it, I need to remember that on my XY table, that the 0 is going to be an open circle. And the reason it's an open circle is because the inequality says just use numbers bigger than 0, don't use 0. Well, the square root of 0 is 0. That was easy enough. Plug in a 1, and again, I'm going to the right, so I have to pick numbers that are bigger than 0. Square root of 1 is 1, and then I'll skip up to 4. Square root of 4 is 2. So now I'm going to go graph those. I'm actually going to use a different color just so we can see the difference between the pieces. So I've got an open circle sitting there from this 0, 0. And I'm going to have a point at 1, 1, and then another point out there at 4, 2. And sure enough, we get our half a parabola. So there's our picture. When you're all done with your pictures, make sure that it's a function. It should still pass our vertical line test. So if I hold up my vertical line, it only intersects my graph once all along its length, including right through here, the boundary. Because we can see that that open circle and that closed circle, because it's open, is not a second point. So it definitely is still a function. So I should never, ever, ever see pictures that look like this. So this is what a lot of people do, something like this. They just graph both of them completely, but it's not a function. Fails the vertical line test. Okay, now on the homework, once you've got it graphed, I would come back in and find the information. So again, graph it first, then find the information. So what we want to find is the domain, the range, and then any intercepts. And then the book is also asking whether or not it's continuous. So is that a continuous function? So, okay, so let's tackle the domain first. Domain is left to right. And in terms of our picture, because it starts over here with an arrow and ends over here with an arrow, we're really going to go from negative infinity to infinity. So does that make sense to everybody? So even in the middle of this, because there's a closed circle on an x value of 0, we know that x value of 0 is still being used. So yeah, domain is from negative infinity to infinity. The range is the sneaky one. So we're going to go from negative infinity to -1 with a bracket. That's this left piece is going from the bottom to that -1. The graph then takes a break, picks up again at 0, and goes off towards positive infinity. And because it's an open circle, we'll use a parenthesis on that 0. So we can see that that little gap right there is playing into that range. Okay, in terms of intercepts, it has no x-intercepts. So no x-intercepts. And the y-intercept is down there at 0, -1. And it's not continuous. And the reason it's not continuous is I cannot walk along this without having to jump or fall. So I walk along it as a little bug, and I'm here, and I can't get to this piece up here without having to jump. So it's not continuous. I cannot retrace it without lifting off my marker. So, and that's your first piecewise function. Any questions?
There's not an intercept at 0, 0 from
No,
square root of x.
Circle. Yep. So and those open circles are going to cause the problem. So that's why there's no x-intercept, because it's open.
Gotcha.
Okay. Okay, let's go try another one. I think you guys have 4 to graph, 3 or 4. Okay, so our next one, same directions. Once we've got it graphed, we're going to find the domain and the range, talk about the intercepts and continuity. So example 3 says f of x is equal to x to the 3rd, and that's if x is less than 2. I'm going to get a -1 if -2 is less than or equal to x less than 5. So this one has more boundary numbers floating around than the last one did. We'll do the same kind of analysis though. So that x cubed is piece 1, and it's my left side. And you know it's the left side for multiple reasons. Functions are always written in numerical order from left to right. So because this piece is written first, it's the left side. But also because the inequality is pointing to the left, it's less than 2. So piece 2 over here is going to be our right side. That's our right side. In terms of what they are, well, x cubed we just saw was one of our toolbox functions. So we know that this is going to be that S shape. We're going to have to plot some points to figure out exactly where the S shape is. This -1 is a constant, so we know that this is a horizontal line. Okay. So and again, just helps if you've got some idea of what you're doing before you go and do it. Okay, let's go talk about piece 1 then. The boundary number for piece 1, so this is the left side. And what we're plotting is y equals x to the 3rd. The boundary number I'm going to start abbreviating as BN for boundary number is at 2. So when I go to build my table, the very first number I'm going to plug in is that 2. So whatever boundary I have, I automatically plug it into the table. Very important. But because this boundary number is going to be an inequality that does not include the equal to, I'm going to write myself a note that that is an open circle. So when I go to graph it here in a minute, I'm going to have to make sure it's an open circle on the picture. Okay, let's just plug in 2. 2 cubed is 8. That was easy enough. But I need more points because this is not going to give me enough of a shape. So it is the left side. So that means we need to pick numbers that are to the left of that boundary number. So numbers that are less than 2. I'm going to plug in a 1. 1 cubed is 1. We'll plug in 0. 0 cubed is 0. We'll plug in a -1. -1 cubed is -1. I don't know that that gives you enough or not. I'm going to go ahead and plug in -2. -2 cubed is -8. That's enough to give me my picture. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so at 2, 8, we have an open circle. We've got 0.11, we've got the origin, -1, -1, and then -2, we're down here at -8. And we can see, sure enough, the S shape is sitting there like that. So there's the left side. I didn't leave enough room for my right side. Any comments about it? So again, establish where your boundary number is, use it as the first number in your little XY table, determine whether it's open or closed, and then go to the left side. Okay, so for the right side, so piece 2, we're going to do y equals -1. Now it's got 2 boundary numbers in it. It's got both a -2 and a 5. So notice I picked both of those up. So in terms of, well, wait a minute. I got a typo somewhere. Nope, I can't apparently copy. That is not a -2. Get rid of that. And I knew that because all of a sudden that was to the left of the +2. So don't do that. Okay, so the boundary numbers, sorry about that, are 2 and 5. So we're going to plug in both the 2 and the 5. Is the 2 going to be open or closed according to those inequalities?
Closed.
Yeah. And what about the 5?
Open.
Yeah. And again, if we were actually face-to-face in the classroom, I would be doing a lot more pausing and a lot more waiting. But I know that watching the computer is not the same thing as watching a live version of this. So, okay, this is interesting. When I plug in 2 to my function, there's no x to plug into. So no matter what number I plug in, I'm going to get a -1 out of it. When I plug in a 5, I'm going to get a -1. And because this one is bounded on the upper end at 5, I'm not going to try any numbers larger than 5 because the graph has to stop at 5 in terms of x's. So literally that's enough to do it. We've got everything we need. So I'm going to go plot those points. So at -2, we're down at -1, it's open. At 5, we're down at -1 and it's closed. So it's a horizontal line going between those 2 points. Whoops, I did that backwards, didn't I? Well, I'm sure you guys caught that. Left side's closed, right side's open. It's not that I couldn't have 2 open circles. I could. Okay, there's nothing wrong with that. It just, that's not what this one is. So the closed is on the left side, the open's on the right side. And there is your piecewise function. I'm going to go ahead and put an arrow on this end to indicate it goes on. Okay, let's go find the information. So what is our domain? Everybody got a guess? In terms of the x's, what x values are we using?
-infinity to infinity.
So it is -infinity on the left side, but does the graph go off beyond the 5?
Oh,
Yeah. So we're going to use a 5 with a parenthesis. This is hard. I mean, we don't have a lot of practice under our belt yet. So, okay, what about the range? So where's the top of the graph stop at? 8. The arrow down here is going off towards -infinity. So we're going to go infinity to 8. Yep, beautiful. Notice that the one piece includes all the y values for the other piece, right? So the left piece, the curve, is including the y value that's on the right side. So you're not writing a domain and range for each piece. You're writing it for the overall function, and that takes a little getting used to. So in terms of intercepts, everything's at the origin. So both the x and y intercepts are at the origin. And again, it's not continuous because you cannot trace it without lifting your pencil. So. Whew. Comments or questions? They take time. They are not short problems. It takes a while to process it through. So let's try another one. So example 4. This one actually has 3 pieces to it. So f of x is equal to, I have -x minus 3, and that's for x less than 3, less than -3. I have 9 minus x squared. -3 is less than x, less than or equal to x, less than 2. I'm trying to make sure I copy better than I did on the last one. And I'm going to get a 4 here if x is greater than or equal to 2. Okay, and then I'm just going to double check to make sure boundary numbers are the same, right? So these are both 2, these are both -3. I've got an equal 2 on a -3 and an equal 2 on a 2, so we're good to go. So this time, instead of just a left and a right, I have a left, a middle, and a right. So piece 1 is going to be the left. Piece 2 is going to be the middle. And piece 3 is going to be the right side. So when we look at them and are trying to figure out what each of our pieces are, this first piece, because it does not have any exponents, radicals, x naught in the denominator or anything, we know that that's going to be a line. Our second piece has got that x squared again, so we know it's going to be a parabola or a U shape. The last piece doesn't have any x's, so it's a constant, so we know that it's going to be a horizontal line. So we kind of have an idea of what each piece looks like. So let's come in and tackle them one at a time. So piece 1 is y equal negative x minus 3. Its boundary number is negative 3. So we're going to plug in a negative 3 into that xy table. And because of the inequality, we'll make our note to ourselves that it needs to be open. Okay, we're going to plug in a negative 3. Watch your signs carefully. So this is the opposite of a negative 3 minus 3. So that's positive 3 minus 3, which is 6. No, which is 0. Don't do that. You get a really wild looking graph. So, okay, now what other number do we need? Well, we're picking numbers that are on the left side of negative 3. So let's plug in what? Negative 4. So that would be the opposite of a negative 4 minus 3. That's going to give me a positive 1. And because it's a line, that's all you need. 2 points to find a line. We've got 2 points. We're good to go. So way over here, I'm going to go graph what I've got. So I've got negative 3, 1, 2, 3. I am at 0. It is open. And at negative 4, we're up at 1. And because it's the left side, I know it's going to go off like this. So again, draw it to the left. Start at the boundary number and go to the left. Okay, any comments or questions about that? Okay, piece 2, right smack in the middle, is y equals 9 minus x squared. And this one's got boundary numbers starting at negative 3 and going off to 2. So that gives me a nice range of numbers to use on my little chart. So I have x, I have y. We're going to start at negative 3, and the last number we're going to plug in is a 2. And I don't know what I'm going to do in between, but I'm going to leave room. What about the negative 3? Is it going to be open or closed? So I go back to that inequality. We know the negative 3 is going to be
Closed.
And 2?
Open.
Yep. Okay, so if we plug in a negative 3, that would be 9 minus a negative 3 squared. Negative 3 squared is a positive 9. 9 minus 9 is 0. I can plug in the 2. That would be 9 minus 2 squared. So 2 squared is 4. 9 minus 4 is 5. Okay, I want a couple more points because I know it's a U shape, but I need to know exactly where that U shape is sitting. So let's go ahead and use negative 2, negative 1, 0, and 1 and plug all of them in. Normally I wouldn't do that, but just because it's so new to us, we need that practice. Okay, so plugging in the negative 2, that'd be 9 minus a negative 2 squared. It'd be 9 minus 4, which is again 5. Not worried about it. It's a parabola. We should see repeated values. 9 minus a negative 1 squared, that'd be 9 minus 1, which is 8. Plug in the 0, I'm just going to get a 9. And if I plug in the positive 1, I didn't leave myself enough room, but I'll get an 8 again. Huh. Okay, let's go plot all that and see what we've got. So at negative 3, we are at 0, and it is closed. Well, wait a minute. We'd already shown that as an open circle at negative 3, 0. So piece 2 is going to come in and take that open circle and close it in, which is great for continuity because now all of a sudden I can trace right through that. So there's nothing wrong with filling it in. At negative 2, we're up at 5. 5. 2, we're at 5. At negative 1, I'm up at 8. 7, 8. And at 9, I'm sorry, at 0, we're up at 9. Huh. Okay, and then at 1, we're back down at 8. So at 1, we're back down at 8. And at 2, we're back down at 5. And that needs to be open. So now we're going to put in an open circle at 2, 5. So sure enough, it's a parabola, and hopefully you hit your points better than I did mine. Graph paper helps a lot here. There we go. But it's a parabola opening down, which we would not have known. We will definitely talk about that next week. And why this is opening down is because the x squared has got a negative in front of it. So that negative on that x squared is going to flip it, which we will discover next week. So cool. So far, so good. Here, what about piece 3? So piece 3, squeeze in here, is y equal to 4. And this, again, the boundary number is at 2. So we're going to plug in the 2. In this case, it is closed because of that inequality on the 2. So if you plug in a 2, this is automatically saying you're going to get out a 4. And I don't know if that's enough to give you what's going on or not, but any other number you plug in, so if I plug in a 5, I'm going to get out a 4. If I plug in a 6, I'm going to get out a 4. If I plug in 100, I'm going to get out a 4. So again, it's a horizontal line sitting up there at 4. Okay, so we have a closed circle at 2, 4, which does not match up with the other one, and then we have a horizontal line going on to the right. And there is our piecewise function. That is an ugly piecewise function. That's as hard as they're going to get for you. Okay, so let's talk about the information in terms of this. So what about a domain? So from left to right is every x value being used.
Yes.
So negative infinity. Okay, what about my range? So the range is the bottom to the top. Well, the bottom of the graph is at 0, and it's a closed circle, so we know to use a bracket. Okay, the top of the graph is up here at, what, 9? It's also closed, so I'm going to use a bracket. And then I want to make sure that all possible y values are being used. So the red piece that's in the middle is using all possible y values between 0 and 9. So even though there's an open circle on this side, the closed circle on this side at 5 means that 5 is still getting used. Everything between 0 and 9 is getting used. Okay, in terms of intercepts, again, I'm just going to pull them from the picture. I've got an x-intercept at -3, 0, but only the 1. The y-intercept is sitting up there at 0, 9. And again, that's why I would graph it before I go find any of the information. It's still not continuous. I had high hopes that when we filled in that first circle that it would be continuous, but because there's a gap over on the right side, it's not continuous. So, whew. And if you can kind of follow that one, you're right where you need to be to do these. So, okay, and then we're gonna do one more and call it good. We're gonna do the go backwards problem. So we're gonna start with the picture and try to write the function. And we will do this every chance we get because I think it really helps understand what's going on. So example 5 looks like this. 1, 2, 3, 1, 2. I've got a point over here at -3, -2. And then 1, 2, there's an open circle right there. This is -1, -1. So it goes through like that. And then on this side, it's going like this. So we see the V shape for the first time in a graph. On the other side, we're down here at 1, -4. This is closed. And then I have another point over here at 2, 1. And then I have another point that looks like it's at 3, 4. 3, 4. It looks like this. So it is not a line. There's a little bit of a curve there. And what we want to do is write the equation of that piecewise function. We are going to assume that all the pieces are from our toolbox that we talked about at the beginning of class. So, okay, let's go for the left side first because it's the easiest piece. We know because of the V shape that the left side is an absolute value. The problem is that our absolute value should be centered at the origin. Should be sitting right here, and it's not. It's been moved somehow. So I have to adjust that absolute value. We will talk a lot more about this next week. So let's do f of x is equal to, okay, normally I would just do the absolute value of x, but that's not good enough. We have to move it. So we can see that the graph has been shifted. This point that should have been right here has been moved to the left. So when we graphed our circles, we kind of saw things getting moved left and right. So I'm going to call that x minus 3 and see if that's going to work. Okay, for now. I'm also going to recognize that it's been moved down 2, so I'm going to put a minus 2 on the outside of that. This will not make a lot of sense until next week. The ones you have are all lines. I went to pick one that was just a little bit more complicated as an example for the lecture. I want to test this to make sure this works. So let's just plug in a number. Let's plug in 0 and see if we get the right answer out of this. So I'm just testing it. So here's my check. So let's let x equal 0. So that would be the absolute value of 0 minus 3, and then outside of that a minus 2. That's the absolute value of a negative 3 minus 2. Well, that's 3 minus 2, which equals 1. Well, sure enough, at 0, we have an x value of 1. You could test any other point you want. If you plug in the negative 1, it should work. If you plug in the negative 3, it'll work. Okay, but now I have to recognize when we're using that. So we're using that for x values that are what? Less than 1. So I come up to my picture. I see that this piece is starting at an x value of 1. Because it's an open circle, we're just going to use a less than. Again, how I shifted this, we can kind of see it from the circles, but we will talk more about it on Tuesday. Okay, what about the other piece? Well, it kind of is curved, So this is 1, negative 4. This was 2, negative 1. Is that right? And then the other point was up at 3, 4. Okay, so this, because of its shape, is either going to be an x squared or an x cubed. And I don't know which it is until I try one of them. So because it's not as curvy as a parabola should be, I'm going to call it an x cubed. But I don't know that for sure, and I have to test it. Well, we saw a few minutes ago that on our toolbox function, the x cubed cut through the origin like that. This is not cutting through the origin. So again, it's been shifted. So this time we're going to go to the right. So we'll add a +1. And then I'm going to cube that. And then it's been shifted down 4. So what I'm assuming is that this point right here is the point that should be here and has been shifted over. So let's just test it to see if it works. So let's plug in 1. That's not working, actually. If I plug in a 1, which is what this is, 1 plus 1 is 2. 2 cubed is 8. 8 minus 4 is a positive 4. So that didn't work. So what's going on here is that this piece is probably not the middle piece. That's no good. So in order to adjust this, let's go ahead and shift it down 8 and see if that works. That's still not going to work to get me where I need to be. Looking at my picture thinking, well, this was a bad one to pick. Maybe it is a square. What if we plug in a square and see if that works? Let's try that. So if I plug in 1, 1 plus 1 is 2. 2 squared is 4. 4 minus 4 is still not this point. So it's still not giving me the point I need. But if I plug in an 8 to shift it down, that should work. Because 2 squared, 1 plus 1 is 2. 2 squared is 4. 4 minus 8 is a negative 4. So it definitely fits the first number. We're going to call that good. And this is when x is greater than or equal to 1. So please take this with a grain of salt. I haven't verified those other 2 points, but for now we're going to assume that it works. The ones that you have on the homework are just lines, so they're not as ugly as this one. So, and those are the piecewise functions. It will take a little bit of time, so make sure you give yourself plenty of time before Saturday when it's due to work on it, because you're gonna have to work on it and then go away and then come back to it kind of thing. So again, just a reminder so everybody recognizes that there's no class on Monday. I have a previous appointment that if I reschedule, it's just going to be 4 months out. So I'm just going to go in and see the dentist. So I scheduled it 6 months ago. We're just going to go keep it. It does work out in terms of lectures for next week because we only have 2 sections and it's over 3 lectures for next week. So it works out fine for us. So take Monday off. Don't worry about anything on Monday, but make sure you do your quiz on Sunday. Okay, any other comments or questions about all the function stuff? We threw a lot at you this week, and I know that. So make sure you wrapped your head around it before the quiz on Sunday, okay?
Sounds good.
Okay, have a
Thank
great
you.
weekend. Enjoy it. See you Tuesday.
Thank
Bye-bye.
See ya.
All right, see ya.
Bye.